Yep, looking good.
Okay, well, I'll get started then. Well, thank you so much to the conveners for inviting me. I'm a huge fan of this seminar series, and so it's a big honor to get to stand up here and give one of these. Before I start, I want to just acknowledge my collaborators here: Tyler Doan, Sylvia Nikovich, Christy Ross, Miriam Primus, and Brian Gold, who have all contributed a huge amount to this project. I can't take credit for all of it. I can take credit for the mistakes, so let's move on. But first, I want to have a sort of solemn kind of acknowledgement here that today we're going to be talking about fault scarps. And so fault scarps, they are features that arise as a result of really large magnitude seismic events. And so with that in mind, there are features that we can learn new things about geomorphology from, but I think as scientists, it's important for us to maintain a level of empathy, particularly when these features are associated with earthquakes, which cause very tragic events like that which is happening in Turkey and Syria right now. So let's just start off with a statement like that. Okay, so I like to start really kind of broad scale when talking about these studies. So in geomorphology, one of our broad goals is to take all the complex processes of the Earth and subsume them all down into simplified models that we can use to explain and predict the shape of the Earth's surface. We do this because we want to be able to use these models to extract information about natural hazards or to answer questions such as how will a landscape respond to climate change. Now, in order to meet these sort of lofty goals, we need to have our models be sort of satisfying in their capability to explain phenomena, and we want them to be based on fairly robust physics so that we feel that we have a strong grasp of what's going on or the underlying mechanics of the landscape. However, this is a really challenging goal for us geomorphologists. And part of the reasons for this are that the sort of timescales of the processes that shape the surface of the Earth are often greater than the span of a human observational timescale, or even many human lifetimes. Complicating this further is that erosion erases information that would be really useful for us in a model testing sense, such as the initial conditions of a landscape before a process is acted on it. And the combination of these two things can lead to data being fairly sparse. And it's sort of our grand challenge as geomorphologists to try and overcome this challenge. And so a particular place where this is very true are hillslopes. So everyone here is probably familiar with hillslopes, but they are the sort of upland extensive landscapes that act to convert bedrock material into soil. They range from steep, sharp, crystalline bedrock dominated mountains to sort of convex, gentle, smooth, soil mantled hillslopes like the picture in the back there. Now, there are two kind of big models that I'll focus on today that attempt to explain hillslope geomorphology. The first family are diffusion or diffusion-like equations, in which sediment is sort of treated as a material that's analogous to heat or gas, where the mean free path of movement of a sediment particle is small relative to the observational scale. So, diffusion has the perks that it's very intuitive. It also can create sort of a rounded kind of convex looking hillslopes that we see. And, it has existed, the ideas behind this sort of diffusion thinking have persisted since the time of Gilbert. The second class of models, I'm sorry, one extra thing here. In a diffusion equation, the basic statement is that the rate of change of elevation at a particular point is a function of the slope at the point that you're currently standing on. As to these sort of diffusion models, there are these family of models which are based around non-local effects. And so basically what they say is that the rate of change of elevation at a given point is a function of your local slope, but it's also a function of the slopes uphill of you. And so the idea being that as gravity moves things downhill, factors such as momentum and raveling and so forth can cause that material to, come down and sort of change your elevation locally, even though that sediment may have originated in a non-local source further uphill. The treatment in these non-local models is that sediment is, treated in a probabilistic sense, in that, a grain of sediment sitting on the surface has some probability per unit time of becoming entrained and then set into motion. And then while it's entrained, it has some probability of coming out of motion or being disentrained. And so that kind of conceptual framework can build up a class of different models. So now here's the thing. Both of these models can create pretty hill-slopey looking hill slopes in their models. So a challenge then comes, how do you differentiate between these two models? Well, fault scarps may give us a rare opportunity to do so. So fault scarps are these locations of abrupt topography that appears instantaneously of the result of an earthquake. And so here we're going to focus on normal motion. I always get this wrong. The hanging wall drops down relative to the foot wall, and it creates, just in a matter of seconds, a blob of topography. And so on the left here is a picture of the 1983 Bora Peak scarp resulting from a magnitude 7 to 8-ish earthquake. And then on the left there is a cross section through the scarp, just showing you the mechanics of what's going on here. The red arrows indicating the offset, and the dashed lines kind of showing the movement of mass off of that scarp as it erodes. They come in these fault scarps come in a wide variety of topographic expressions. If you look at any given one across the planet, it can range from something looking sharp, like that one on the left there, to more sort of rounded and more degraded looking, like that picture there on the right, taken from Deep Creek in Utah in the United States. There's generally a relationship between the sharpness of the scarp and its age. So these photos here show photos taken after 2 events. You can see that the scarp itself has a very sharp kind of crest and a cliff face there, which is material that is sort of hasn't been eroded yet. This is something we would refer to as a free face. And then you can also see piles of debris located at the base of the free face to varying spatial extents. Asphalt scarps persist on the landscape for long periods of time. They become further degraded and more rounded out. And so here are a couple of pictures here of fault scarps that are thought to be considerably older. You can see, particularly on that picture on the left there, how the scarp gets kind of rounded out. And so, okay, this is great, interesting, but why does this matter? Well, fault scarps represent an instantaneous perturbation. The perturbation anneals over timescales that are actually pretty useful to us and let us use a lot of different tools, particularly geochronometers. And because it's just a sudden perturbation to a landscape, they function as a natural physical experiment in which we can use to test models against. Now, this is cool because the processes involved in fault scarp degradation are similar or often identical to those acting on hill slopes. These processes can be granular movement, rock collapse, bioturbation, soil forming processes, and so forth. And as hill slopes cover the vast majority of the Earth, we can potentially use these fault scarps to gain some further insight on the overall behavior of the Earth's surface. And, let's move on. Okay, so let's dig into it. So if we look at the topographic profiles of fault scarps, we do see some interesting features. In particular, the crest of these scarps tends to be, the topographic profile of it tends to be much sharper than the toe down at the base. This is true whether you have a morphology that's quite sharp or one that's sort of more degraded in an intermediate sense. And in the more diffuse or highly degraded fault scarp sense, there is a little bit of this here. So I went and I compiled around 500 topographic profiles from fault scarps to see if this asymmetry was persistent across various variables such as substrate lithology or local climate. I've got these guys plotted up here for single event fault scarps on the left and for multiple event scarp profiles there on the right. If you, it's not super easy to see in this. There's a lot of scatter here. if you sort of fold these profiles in half and then plot a trend line onto them, you can kind of see, so this is the green line here is a linearly smooth, less spaced trend line just slapped on there just to see if you can detect this kind of asymmetry. And it appears that you can actually. So full disclaimer here, I've just got this data and started working on it. I'm not totally sure if I've done this part exactly right, but I think if the data were, if these fault scarps were symmetrical in topography, we wouldn't see this pattern in the data here. Why this is significant, if you take these two, this diffusive or non-local model, and you apply it to a fault scarp, you end up getting different forms to them and different symmetries. So the diffusion model, just because of the nature of how diffusion works, your fault scarp topographic profile is always going to be fairly symmetrical about the inflection point or the midpoint of the scarp itself. If you apply a non-local model, you can end up producing scarp profiles that have this asymmetry as a core factor of them. So the diffusion model there is on the left, and the non-local model there is on the right. So this is part of some ongoing work that we're doing right now in compiling all these fault scarps and finding quantitative ways to compare them between these sort of diffuse or non-local model conditions here. Now, I will say many people who are proponents of sort of diffusion or diffusion morphologic dating of fault scarps would argue that the initial phase of a fault scarp evolution is probably dominated by non-local processes, and then over time, diffusion becomes a better approximation of this degraded scarp. All right, so if we're going to dig into this a little further, let's look at the actual structure of the sedimentary deposits that form at the base of the fault scarp. So if you dig into a fault scarp, it's very common to see a particular pattern of colluvial deposits. Paleoseismologists who are very interested in the timing of earthquake events will typically dig a trench across a fault and look for this sequence of sedimentary deposits in order to interpret a sequence of earthquake events. Generally, what this pattern looks like is a sort of a soil that has been buried by a pile of debris, or what they refer to as the debris facies. These consist of coarse, poorly sorted sediment, presumably resulting from collapse of the free face. And then overlying these are progressively finer grained and better sorted wash facies that will have more structure, sort of more bedding to them, and presumably reflect more of the sort of gradual sediment transport, maybe more diffusive-like transport. So from these deposits, we can potentially gain further information on the topographic change over time of these fault scarp profiles. Again, these relationships are fairly consistent across field sites, and the change from debris into wash suggests that our processes are changing over time. So that might be something that we need to consider when we are building a model or testing models against them. So now we're gonna zoom into this field site in Deep Creek in central Utah. This site is I'm going to argue is a very classic example of the fault scarp stratigraphy. It's a simple normal fault that happened around 500 to 700 years ago. And if we go and zoom in onto that area highlighted in the middle, you can see that it has this sort of eye-catching view to it. So some things you may notice right away are this buried soil at the base here, this small downdrop chunk of soil here, a fault scarp or a fault line coming up the side, and then a series of like sort of eye-catching beds, apparently prograding off of the scarp face. If we go and map these out, we can see that indeed it does have this classic structure, a series of debris facies in them, overlaid by sort of wash facies in them. A particularly useful thing here in this particular field site is that due to the sort of flat-lying, platey shape of the cobbles, we can go through and we can map out micro paleo surfaces of the fault scarp, or presumably the colluvium as it is depositing as the fault scarp degrades. So what I've done here is I've gone through and I've mapped in various micro topographic surfaces in here and extracted them. And so what you can see here are, they're sort of colored here. The lighter colors are presumably younger in age, leading up to the older age, higher parts of the colluvium. And we can sort of look at these and sort of compare them. So if we look at our diffusion model, so we're going to be looking at sort of the lower part of the diffusion model over here. Each one of those lines there represents a time step in the diffusion model as it progresses. And one thing that we should note is that these lines should all converge towards the central inflection point of the model, this sort of midpoint of the fault scarp. If we look at our field data, we see that they don't necessarily look like they're all trying to converge to one place. In fact, they have a lot of sort of parallel kind of, they are largely pretty parallel and actually fairly consistent in their thickness. If we compare this against a non-local model, we can see that our non-local model create, periods of sort of evenly spaced bedded layers down in the sort of colluvial pile there. And another point there is that in a non-local model, that sort of midpoint sort of inflection point part will change over time. In a sort of qualitative sense here, it does kind of look like our sort of micro paleo surfaces here kind of agree more with a non-local model. But anyway, so we've got these key observations here that we want to work with. We've got our asymmetry in scarp topographic profiles. We see differences in the colluvial sedimentary faces over time, suggesting that our processes are changing. And then we have this movement of the slope inflection point, which suggests a non-diffusive kind of behavior is going on here. And so now I'm not the best at modeling, but there are ways in which you can capture the complexity of non-local effects with relatively straightforward models to implement. So what I've used here is I took a stab at developing a cellular automaton-based model of fault scarp evolution. I like to think of it, and Greg Tucker will say this too, that cellular automata is like a non-local easy mode, in that you can apply it and you can generate non-local effects without necessarily having to figure out the complex math of other types of non-local equations. So the way a cellular automaton model works is the model is set up as a grid of cells, and each one of these cells can have a different state. In this particular state, there's three main, or in this model that I've made here, there are three sort of main states to consider: empty cells, cells that contain mobile regolith or sediment, and cells that are in situ material. And so you can see down here a series of different processes that happen. The core mechanic of the cellular automata is that cells can transition between different states in a probabilistic manner set at rates and processes that the user sort of defines. So the images down there are taken from Greg Tucker's Grain Hill framework, cellular automaton framework, and they largely take our mature geomorphic transport laws and transform them into a cellular automaton base. So you'll see things that you might recognize in there, like mobile regolith production, or things such as disturbance, which is similar to like a soil mixing or a diffusion-like behavior, in addition to other sort of simple things like collapse, collisional physics, and gravity. Anyway, so if you take these and you run the model on an initial condition, you can actually generate a fault scarp and a colluvial stratigraphy. So these two rows here show two different model runs, starting with a different initial fault configuration. Panel A there, A through C, shows a 60-degree dipping fault. Its initial condition is just a flat free face, and then we've let the model run for a while, and it's eroded and developed a pile of colluvium in its base. And interestingly, sort of asymmetric kind of profile. The bottom row there shows a 90-degree fault initial condition, and it largely shows the same sort of behavior. Interestingly, the inflection point is also moving with time if you look at the shape of where the fault used to be. So if we can actually take this a step further, and we can classify the cells that based on their transport histories. So cells that have traveled fast and traveled far, we can identify them as being analogs for the debris facies. And for cells that maybe have traveled not quite, maybe far, but also very slowly, we can classify them as being more in these wash or sort of better sorted facies as well. So this is all well and good. Creating a model that sort of looks like reality is kind of a first step in doing this. But what we ideally want is a property or something we can measure in our field site that we can predict in our model and sort of directly compare it in a quantitative sense. So here is where we can apply a sediment tracing method in order to have a direct sort of apples to apples-y comparison as we can get between our model and our data. So I'm going to turn here to the phenomena of luminescence. So luminescence is a property of minerals where if you shine light on them or you give them energy in some way, they emit their own light back at you. This light comes from the trapping of electrons by ionizing radiation within the crystal lattice of minerals. So the basic process is that you can imagine a sand grain and its crystal structure. And so that crystal structure is going to be messy and it has lots of defects in them, locations of uneven charge. The electrons just sort of hanging around in there are subject to natural background radiation, which sometimes they absorb and hop up into higher energy states. When they're in these higher energy states, they have a probability of getting stuck within the defects in that crystal structure. And depending on the type of defect, they can stay there for a long time until they receive a source of energy to escape. And typically natural environments, that energy comes from either sunlight or heat or pressure. You could take this concept and turn it into a conceptual model and think of each sand grain as being a little battery, a battery that will discharge when it's in sunlight and it will charge up when it's in the dark. So the basic concept of LSL dating is that we'll go and we'll take a sample, we'll measure how much luminescence is there, and that gives us a value that is a proxy for the time since that sand grain has seen sunlight. Sometimes that's equivalent to a depositional age. However, that's not always the case. Sometimes grains don't see enough sunlight to completely remove all of those trapped electrons. And so if we take measurements of if we perform experiments of sand grains and compare their luminescence versus, say, sunlight exposure time, we can develop a relationship between those two. So the panel on the left here is just a plot of sediment from the Deep Creek site. And I've performed a series of sunlight exposure experiments and then fit an equation to that. And on the right there is luminescence versus equivalent dose, which is basically saying the rate at which luminescence increases while it's in the dark. And so with these two sort of relationships here, we have a behavior that we can model within our cells as they sort of transition and move around in our cellular automata model and make predictions about the distribution of luminescence. So here's what that looks like. If we vary the various process rates, we can create a different distribution of luminescence. So these four panels here show keeping the sort of weathering rate constant and the soil disturbance rate constant, but varying the collapse rate. We can sort of change the distribution of modeled luminescence across colluvial wedge. And so you can see that the higher collapse rate scenarios involve greater amounts of luminescence closer to the fault, whereas lower collapse rate scenarios end up creating much lower luminescence and more sort of well bleached. So, okay, but this is a prediction of a property that typically takes a long time to measure, as evidenced by luminescence ages taking, months to, well, many handfuls of months to turn around. So instead, what we can do here is we can apply a portable luminescence reader. So this is a cool device where you can just pop some sediment into it, close a drawer, turn on the machine, and it spits out a number. So it is a basic sort of a bulk luminescence measurement without much pre-treatment or anything like that. It can't necessarily give you an age, but we can use it in a relative sense to evaluate changes in luminescence across an outcrop. And so with a small amount of pretreatment. So what we did was we went back to that field site and we collected samples in a 10 centimeter by 15 centimeter grid across it. We did this underneath a dark tarp, and then took the samples back to the lab, measured it, and plotted it up. So here's what that data looks like. So each one of those data points there, the little circles, is the luminescence measurement. And then the sort of color map behind it is those values sort of interpolated across using a Creeding scheme. If you look at this, you can kind of see there is a broad pattern of closer to the fault, the luminescence is higher. And then as you move away from the fault, the luminescence is lower. You can also sort of look in this. And so we wrote a paper on how you can sort of interpret these patterns of luminescence across this colluvial wedge here to infer various changes in sediment transport. It's kind of an interesting property of this luminescence because you're measuring the amount of sunlight that a grain has seen as it's traveled, and depending on how it's traveled, it's going to have seen various sunlight. So, you know, we observed things like the sort of free face would collapse and create a debris pile, and then that debris pile would sit for a while and potentially mix and get sunlight exposed on the surface of it before another collapse happening on top. You can see kind of this sort of stochastic structure in there. If you take kind of the sort of distribution of luminescence and you're mapping out and compare it against geochronology, you can work out things like, okay, what are the various timescales of things and how did they occur? We ended up finding that many of the processes operate on fairly similar timescales and can interact with each other, and speculated that this could have some preservation bias issues. But anyway, so getting back to explaining our evolution of fault scarps, we found that our model, this sort of non-local cellular automata model with our sort of moderate collapse rate, could actually recreate the field data, the luminescent sediment tracer fairly well. And I think it built a case here that these non-local effects actually matter quite a bit in geomorphic environments. And they are something that we should take seriously, and we should consider implementing these more. All right, so I'm going to move on to the takeaways here. Fault scarps can be topographically asymmetrical. This asymmetry appears to persist for fairly long timescale methods, suggesting that non-local processes are involved. The sedimentary facies indicate that we have a variety of processes that are acting on it, and they may be different enough from each other that it could be hard to subsume them into something like a diffusivity. Our sort of micro paleo surfaces within the colluvial wedge also sort of support a non-local kind of perspective. So if we take all of that together, it might suggest that non-local models better explain the full evolution of fault scarps over their entire lifespan. And as such, we may consider that maybe this is evidence that these are better models to be applied towards hill slopes rather than diffusivities. So future work that we have that we're working on right now, that compilation of fault scarps I showed you earlier, we're working on our statistics and our data analysis of that to see if we can detect things like changes in the various moments of slope over time. And our end goal, or one of our goals, may be try and develop a new scarp morphometric dating method using non-local physics. Anyway, yeah, so thank you so much for having me and for listening to me blab on. Thank you to the Utah Geologic Survey for helping us out in the field. And please feel free to email me with questions, or I'll also be on the Discord. So thank you very much.
Thank you so much, Harrison, for this really, really cool talk. I really enjoyed. I remember as a first-year student in geomorphology learning about this diffusion model and thinking, does it actually work? And it's really, really cool to see actual results.
Yeah.
So it kind of works, I suppose. The chat is now open for questions. If anybody would rather speak out, please raise your hand using the reaction button, and yeah, we'll unmute you.
Yeah, it's kind of interesting. Like, if you go out into the field and you look at sediment moving around, like it really is diffusive sometimes, and then sometimes it's not. And so it's kind of fun to play around with the different ways that it could be happening.
Yeah, Bob Anderson, go ahead.
Harrison, that was a lovely talk. I love the inclusion of the modeling, and now this OSL with this portable reader is just spectacular. So I have a question, and the question is, when we have tried to deal with this kind of asymmetry in the past, what we've appealed to is the decay of cohesion in the materials that had to be overcome before they're freed off the face. So in that case, we're dealing with two problems. One, effectively the weathering that then releases the sediment, and then two, the transport of that sediment. In the past, we've simply used a diffusive rule, perhaps with a roaring like, enhancement as you approach a critical slope. But can you address how you incorporate the decay of cohesion, if that's important in these models?
Yeah, absolutely. So a cellular automata model is like really useful for answering that type of question, because you can customize the various states and you can get them to act differently. So if you wanted to have like a fault scarp with a sort of carbonate soil that's really cemented it together on top, it would be excellent for doing that. It also, in the sense of, how might you solve a sort of continuum formulated non-local model, where you're doing the integral of the flux uphill, it could be pretty complicated to try and do that. But the cellular automaton might be able to handle that. Having a model that lets you handle all those different types of complexities is quite fun and quite useful. But deciding like sort of general things from it. Yeah. Anyway, does that answer your question? Sweet. Thanks a bunch.
Okay, thank you. And if anybody else has any more questions, of course, feel free to raise your hand. Meanwhile, I see. All right. Yeah. Sorry. Go right ahead and unmute yourself.
Okay.
Kevin.
Thank you, Harrison. I'll echo the praise for that talk. I learned a lot. Thank you. I have a question. If a fault scarp happens in a really flat landscape, that will be very different than if it happens on a hill slope. Here in New Mexico, many of our quaternary fault scarps are on steep alluvial fans or at the base of mountains. Are you thinking about in the future adjusting these models to what the landscape is, what the relief is or topography is prior to rupture?
Absolutely. Yeah, that's a great question. And in fact, some of the initial work on fault scarp diffusion dating methods really made the point that the far field slope does matter a lot. And in particular, if you're forming a fault scarp on a sort of slanted environment like that, as that sort of angle of the alluvial fan increases, you have a greater probability of ravel and things coming from further up, coming down and affecting your fault scarp, your topography and your colluvial stratigraphy. My sense is that as things get steeper, the more non-locally you need to think about these sorts of things. If they're sort of flatter, you can potentially maybe what's going on right on the scarp is going to be very non-local and very ravelly, but maybe the transport that's occurring right on the crest may be more diffusive. Maybe it's more affected by rain splash, or maybe the gophers are digging around and just moving sediment from various place to place, sort of locally around. That's definitely something to be further explored. Yeah, but it's a great point.
Okay, any more questions from the audience before we move on to our chat?
I did stick my hand up.
Sorry, Michael Kirby, go ahead.
Hi, I very much enjoyed your talk, Harrison. That was great.
Oh, thank you.
I think I've always thought about these things in terms of the travel distance involved in all the different processes, which comes to the same thing as the non-local analysis. I've always been worried about the non-local things, which sometimes seem to have infinite ranges of application, which I don't think are necessary, really. I mean, obviously there is a tail, but it's a well-behaved tail, let's say.
Mm-hmm.
But you know, you've got a mixture of processes, creep type diffusion processes, wash type processes, particularly on when the overall slope is steep, and gravity processes, and all of those are beautifully expressed in what you've seen. It was really great. Thank you very much.
Oh, sweet. Yeah, absolutely. I really appreciate that. You know, I really like that we can have a like sort of broad family of models to try and compare against, and you know, I think it makes the science really rich, and I think it creates some really fun, stimulating conversations.
Well, yes, but I mean, I think, you know, you've shown some tools that really help us to try and properly evaluate and calibrate some of the models we've been playing with more theoretically.
Absolutely, yeah. Yeah, I do think that this luminescence sediment tracing method can be pretty powerful in certain environments, and I think there's a lot of potential there to be explored. So,
yeah, it looks great.
thank you.
I was about to read out the question of Anne Evans. That's a good transition, but I see that your hand is raised, so please go ahead.
Yes, it relates maybe to the previous one, because I wondered whether you have related this work on fault scarps to the previous work on abandoned sea cliffs, which was by Savagear originally, and then a very interesting later paper by Mike Kirby himself.
Yeah.
Thank you.
Absolutely. You know, and I chose to focus on fault scarps here because I felt that they were a very well-defined initial condition and a creation of topography that was very instantaneous.
Mm-hmm.
And when you have terraces that are resulting from some level of sort of marine or sort of fluvial incision, there's the possibility for reoccupation of the cliff face or other sorts of sediment transport processes going on. So I haven't done that direct relationship between the two, but my feeling is that the concepts are probably very portable between sea cliffs or fault scarps here.
Mm-hmm.
And in particular, I think Bob actually did some work in the past looking at the marine terraces off the coast of Santa Cruz, which in some cases do have the asymmetrical like sort of scarp morphology to them.
Yeah, they do, and you're actually seeing bedrock exposed there. So and it's nice smooth bedrock. So it's not something I don't think that the cellular automata would handle well. But it is an interesting question, this business of, okay, we're going to go from the evolution of a steep thing that's made of colluvium to a steep thing that's made of maybe bedrock with a colluvial or you know, a beach cover on it.
Yeah, I think we can probably take the concepts and bring them over, but it might need more dedicated study to figure out where the nuances are in you know, taking on locality and applying it to these different landscape features.
In that Savagear paper, to go back, which is obviously on a much bigger scale than the fault scarps you're talking about, and where the basic surface is bedrock, then one of the parameters in there was essentially the rate of free retreat of the bedrock, which in a sense is, I suppose, coming back to what Bob was saying about cohesion and trying to deal with it.
Yeah, absolutely. It does make sense that the cohesion is probably a very primary control on many of these morphologies.
Sure.
Great. I have a question from the Discord that might be that will bring us to more of a technical aspect, which is by Claire Rollins-Gilder. And she wonders if the OSL has to be calibrated or recalibrated for each location, since the lithology and the surrounding radiation exposure is probably different between sites.
Yeah, absolutely. This is 100% true. So some of the method details I didn't get into on applying the luminescence method there are related to those things. So if we are looking at in that particular field site, there was one lithology that alluvial fan was sourcing a particular unit upstream. So it was fairly uniform across the environment, which let us, do a fairly, apples to apples comparison between, across the outcrop. Now, if you have changes in the lithology, that sort of breaks down. We also tried doing things like precisely laying out each sample and performing a couple of steps of pre-treatment to try and make these, the different sort of aliquots of sample as comparable with each other as possible. But certainly, the sensitivity, the amount of luminescence you get per unit absorbed radiation dose, it changes by so many different factors. So if you're going to apply this method, you either need to be very mindful of these things and pick sites that are, that work with the assumptions of the luminescence method there, or do a more complicated luminescence technique where you're doing a full pre-treatment and you're correcting for the luminescence sensitivity and so forth. But yeah, absolutely, it's a great question.
All right, thanks. And maybe you'll see the question on Discord later, and maybe you can post some links to the relevant publication. I think it's really cool to see how far we can go with these new approaches.
Absolutely, yeah. I'll come join the Discord and answer questions too. So.
Okay, we have a question in our chat, new question in our chat by Philip Johnson, who thanks you for the great talk. And he says that he wonders whether the asymmetric aspect of the profile might result from the contrast in density between the in-place preface material and the lower density scarp delivered colluvium. Do the models take that density difference into account?
Yeah, another good point. Yeah, absolutely. So the packing, in that particular field site, the grain packing due to the deposition by the alluvial fan is going to be a certain way, and then the colluvial deposition is probably going to be more chaotic, and potentially more pore space. We didn't actually look for this. Qualitatively, I do remember from the field site sort of digging at it and it being much more looser in the colluvium than in the alluvial fan. Do the models take this into account? No, they don't. You could potentially figure out a way to do that. For where we got, we didn't include this factor, but we got what I thought was a fairly satisfying recreation of the field site. And so, maybe by inference there, it doesn't have a huge effect, but it probably could, depending on the question that you're trying to answer or the specifics of a field site. It's a good point.
IDT.
Yeah, sorry, I still haven't managed to make my video work, but I had a question. So just out of curiosity, I mean, since you're measuring the natural luminescence, right? So just luminescence emitted out from sediment. Then you would expect, like in older faults, to at some point reach saturation, right? If it's a really old fault scarp, so you might expect that there will be saturation, and you will basically be seeing a very saturated signal throughout. So there's no change.
Yeah, that I think it could be possible, except that the portable luminescence measurements are dominantly on feldspars, and so
okay.
It's a mixture of many different minerals in there, but the stimulation wavelength is with either IRSL or with blue, and in the IRSL signal, it's dominantly feldspar, but in the blue signal, my own experience is that feldspars are very bright compared to quartzes when it comes to when they're stimulated with blue light. So my feeling is that the samples are pretty dominated by feldspars. And if that's true, feldspar luminescence dating can go back many, 100,000 years, hundreds of thousands of years. So that might be a longer time scale than the actual, preservation of that colluvial package or the fault scarp itself may be. Now, no one has actually tested if there is an endpoint to these. To my knowledge, no one has tested if there is a saturating point with the portable luminescence measurements. There probably is, but I'm unaware of it.
Oh, okay. Yeah. No, I was just wondering. I mean, because I was wondering if you were measuring like the IRSL, or were you giving like a IRSL before and then doing an OSL measurement just to get quartz out? But it's just an overall measurement with blue light, right? Like it's everything, the entire signal. Okay.
Yeah, it's just
That's great.
unheated sample, 60 seconds of IRSL measurement, and then 60 seconds of blue light stimulated luminescence with dark counts sort of dispersed.
Yeah. Okay. Yeah. Sorry to go into a bit specific question.
No, it's
yeah.
Don't think we have new questions yet, so I might just slide in with one of my own. When we think about the transport of that colluvium that is going to fill the downhill part of the scarp, is it okay to assume that the luminescence signal will be fully reset, or is there also a transport mode that is going to be more conducive to a full reset, and some other type of transport that might, if we move things in clumps, that will be less likely to reset everything? Could you comment on that?
Oh yeah, absolutely. So yeah, basically what we are looking for in this particular example is the degree of resetting across the landscape or across the outcrop, with the sort of interpretation that the fast traveled sort of collapsed material has seen, very little sunlight, versus the sort of slower transported material, like the wash material, that actually may see much more sunlight and thus be more reset. And so, part of the application there is the use of the cellular automata model to have those sediment cells that have different rates of transport, so we can kind of, model the luminescence and see what the distribution should be across there. The broader method of luminescence sediment
Thanks.
is looking at those patterns in reset or not resetness of the grains. Sweet, thanks.
Okay, I think I want to thank everybody who participated in this lively discussion. It was really interesting in addition to the talk, and I want to thank Harrison again for this really fun and interesting talk. And unless there are any more questions, thank you everybody for coming. Feel free to, if you think about anything else, to use our Discord page, and we hope to see you next week.